Welcome back to module 2. We are continuing we are trying to find out how trajectories can be constructed in quantum dynamics, and we are going through Ehrenfest theorem. We have seen that average position is following classical trajectory in quantum dynamics. Similar way, we can follow what would be the average or the expectation value of the momentum, and we can calculate it very easily right now because we have seen the derivation for the position space. So, similar derivation can be used for the momentum, and we will be able to write down this directly: I by h cut minus infinity to plus infinity psi star h p minus p h dx. Previously we had position space, this is x because it is one dimensional we are working on. Previously we have seen similar expression for x, and we have proved it that this is the expression we can get it. So, we have directly written it, little bit of derivation can be done, and because h is a Hamiltonian operator which can be written as second derivative of with respect to position plus v. Again we are considering the time independent potential, and because px is nothing but minus I h cut we can write down first, as we did before. First we have to find out this commutator, and if we know the commutator, then we will be able to get the solution. So, first part of the commutator is, which is nothing but minus h cut square by 2m minus h cut psi, which is nothing but I h cut cube by 2m, this is cube, minus I h cut v del x psi, and the other one, that is pxh psi equals minus I h cut minus h cut square by 2m psi, which is again minus I h cut v minus I h cut dv dx psi. So, we get these two expressions, and ultimately we are interested in this commutator. That is why we have to find out minus px h psi. This is going to be subtracting these two expressions. If we subtract it, we see that this part will be cancelling out, this part will be cancelling out, remaining part is this one. So, this is going to be I h cut first derivative of the potential psi. So, now we can plug that in here, we get d dt of d dt of we have to plug that in, and we have this d dt of px is I by h cut minus infinity to plus infinity psi star I h cut dv dx psi dx, which is minus infinity to plus infinity psi star dv dx psi dx. Again we have got a typical form of the expectation value, but this time it is the expectation value of the derivative of the potential, and that is why we will write this. Change of the momentum is the gradient of the potential, but we have to remember this is not like this. The form is not like this. Form is the derivative, expectation value of the derivative of the potential, and this is something which we study in classical mechanics very frequently. Force is nothing but dv dx, negative gradient of the potential is given by force, that is in classical mechanics. Similar thing we are getting here in quantum mechanics, which shows that the expectation value of the momentum as a function of time, that derivative will depend on the spatial derivative of the potential, negative of the spatial derivative of the expectation value of the negative derivative of the potential. So, these two equations comprising the Ehrenfest theorem, how the expectation value of position and momentum is changing in quantum dynamics. And based on Ehrenfest theorem, the example which we have shown before, the dynamics of the particle, probability distribution, particle is moving, that is why probability distribution is changing as a function of time. In this 3D plot we have given the change, we are showing the change, and if we take the expectation value at each point, I get expectation value at each time, then I get a single point in the position space, and that points, if I plot them and connect them, I get the trajectory of the particle. But this is not a trajectory of the particle, this is the trajectory of the mean position of the particle calculated from the probability distribution function of the particle. So, some kind of trajectory can be constructed with the help of Ehrenfest theorem. We have understood that a practically realizable interpretation of the wave function is obtained only by using the concept of probability density. Probability density, which is expressed as rho xt, is nothing but psi star psi, and we have to get the probability density idea, because that is the only way I can get the practically useful interpretation of the wave function in quantum mechanics. This probability distribution function, I have also mentioned that at t equals t1 time, the probability distribution function can be like this, and at t equals t2 time, probability distribution function can be like this. When the probability distribution function is changing as a function of time, it is manifesting the quantum dynamics. This is the x space. So, probability distribution function has to change as a function of time to manifest a quantum dynamics. And this idea that probability density is changing as a function of time, this idea can be reviewed in terms of hydrodynamic formulation or hydrodynamic flow or liquid flow through space. One can say that as if probability is flowing through space, because see, probability density has changed. The maximum density was here, now maximum density is here. So, this has changed the position. So, as if probability is flowing through the x space or the position space. So, one may conveniently represent the time dependent change of the probability density at a particular position x as a flow of probability density through that point x, if we consider the liquid flow, as if liquid is flowing through space. And this idea will give me the local conservation of probability. Global conservation of probability we have seen. Global conservation of probability is total probability density has to be constant at any time. So, first derivative with respect to time is going to be 0. That is the conservation of total probability density. But local probability density, at this point locally probability is changing. For example, here probability was high at a particular time, then on the same time on a different time, at a different time on the same point the probability density has changed, as if there is a big wave of liquid was here and then now that wave has gone out, and that is why I have less amount of liquid at this point, and that is why at a particular point liquid is flowing through that point as a function of time. So, the flow of probability density through a point is called probability current, which is expressed, this is called probability current, which is expressed by this expression. This expression has its origin in quantum electrodynamics. We will not go over that origin, we will use this equation, this representation of the probability current, and we will try to find out hydrodynamic formulation of TDSE. This is another formulation, another way to look at the time dependent Schrodinger equation. In fluid dynamics, volumetric flow rate. So, let us say a volume of liquid is flowing through space. This is A, cross sectional area, and this is V, volume, V is the velocity. So, per second it will make V distance advancement. So, this is called volumetric flow. And this is 3-dimensional volumetric flow, but if we consider the same thing, if we equivalent form in 1 dimension, then this flow is nothing but the velocity, because in 1 dimension I do not have cross section. So, it is just the velocity, is representing the velocity. So, J, this probability current in 1 dimension is simply representing the velocity. Velocity of the probability going through the position space. What is the velocity with which this probability is changing as a function of time or flowing through this space as a function of time? So, that is the kind of hydrodynamic formulation, the basic idea behind the hydrodynamic formulation. In order to get that, what we will do, we will start with TDSE, time dependent Schrodinger equation, and then we will multiply this equation by its complex conjugate of the wave function from the left hand side. So, I will write down this one psi star dt equals again psi star h psi. I have multiplied this equation by this complex conjugate of the wave function from left hand side, and so I get this equation, and its complex conjugate of this equation would be minus I h cut dt equals h psi star. That is the complex conjugate of the TDSE, and for that also I will multiply real part of the wave function, real form of the wave function, not real form of the wave function, the wave function equals psi h psi star. And remember, this h is a Hermitian operator, which is expressed by again time independent potential we have considered. So, we will this one will be subtracted from this one, we get I h cut psi star plus I h cut psi star t equals psi star psi minus psi h psi star. So, this is the subtracted form. I am just subtracting these two expressions. After this subtraction, I will further reduce the equation by inserting the Hamiltonian operator here. So, I have this is equals to psi star dt plus psi with respect to time is going to be 1 by I h cut psi star h psi minus psi h psi star. I will plug that in, that Hamiltonian operator. So, I have 1 by I h cut then psi star minus h cut square by 2m plus v psi minus psi h cut square by 2m v psi star, which is minus h car square by 2m psi star plus psi star v psi minus h car square by 2m psi dx2 v psi star. So clearly we are going to cancel these two because potential is a multiplication operator. It can be placed anywhere. I can reorganize that expression without any constraint. So finally what I get is I h cut by 2m psi star minus psi this is the expression what we get. Now this part can be written as first derivative of psi star psi, which is nothing but this one. Now this part can be further reduced in following form. I take the negative of this first derivative I h cut by 2m psi star x minus psi star and we know that this part is what we call the current, probability current, which is expressed by jxt I h cut by 2m psi star. This is the probability current. So I can replace it by probability current and I get this expression where density is here and this part is here. So this equation is another form of TDSE. It is called equation of continuity, which shows that how local probability changes as a function of change of probability density as a function of time. It will depend on the negative gradient of the current. So what does it mean? The meaning can be very easily realized if we consider a finite space between x1 and x2. We will show that how within this space in this X diagram, within this space how probability is changing, that we will calculate. But before we do so, one thing we should remember that this is the hydrodynamic formulation of TDSE or equation of continuity. Although the equation of continuity is just another mathematical form of TDSE, but there exists an important difference between the equation of continuity and TDSE in the sense of interpretation. The equation of continuity, as shown here, directly deals with the probability density, which is an experimentally realizable quantity. But TDSE is dealing with wave function and wave function cannot be observed directly through experiment. It is the density which we can directly observe. So, the presentation of or equation of continuity is something which can be directly connected to the experimental observable. So, that is the major difference we have. Otherwise, they are just simply they are different form of the different mathematical form of the same hypothesis, quantum mechanics. Now, we will try to understand this equation, the meaning of this equation, and it will be very easily can be clarified if we consider this finite space between x1 and x2. So, then we can find out the total probability of finding the particle in the x1 x2 space, and that is called local probability. It is not going to be 1 if it is if the wave function is normalized, because it is within this finite. So, I will have an integration x1 to x2 psi absolute square dx. This is let us say p12. P12 is the probability between this in this space, and this is not going to be 1, because 1 I get the probability entire space when I integrate, then I get the probability 1, because I have one particle. So, this is the probability, and if we try to find out the temporal change of that probability, we get x1 to x2 temporal change of the probability like this. Now, we know this form, this is nothing but the change of density as a function of time is related to its current. So, we will be able to replace it x1 x2, this is going to be current dx, which is nothing but x t x1 x2. So, I can find out j, this is going to be x1 t minus j x2 t, and if I consider that j x1 t is greater than j x2 t, then this part is positive and this part is positive. It means that d dt of p12, local change of probability within this space, is going to be positive, is developing the probability within this space, local probability. So, what does it mean? At a particular time, at this point the current and at this point current, they are different, let us say. If the currents are different, if they are equal, then there is no effective change in the probability here. Probability is not changing as a function of time. But if they are different, and if we assume that current which is entering into the space and exiting into out of the space, if these two currents are different, then there will be probability accumulation in this regime, and that is exactly what does it mean. It is exactly the meaning exactly transferred from the fluid dynamics. Let us say I have a liquid which is flowing through this tube, but this tube has large diameter here, small diameter here. So, there is a current difference now, and if the current here is greater than current here, then there will be an accumulation of liquid here, and that is exactly going on here also. The current entering the regime and the current going out of the regime, they are different, and current in one dimensional space is nothing but the velocity. So, the velocity with which probability entering the space and the velocity with which the probability going out of that space, that particular regime, is different. And if the entering velocity is higher than the exit velocity, then in this regime there will be a development of the probability density, development of the liquid, development of the probability density. So, probability density has very close resemblance with the liquid, and that is why it is called hydrodynamic formulation of TDSE. We will stop here. We will continue this session. We will continue this module in the next session. In the next session, we will consider Bohemian mechanics, which is the last topic of this module. We have studied Ehrenfest theorem. We have just now studied hydrodynamic formulation of the TDSE, and the third topic is going to be Bohemian mechanics, which can also give us the trajectory feelings in quantum dynamics. We will meet again.